Good afternoon, students. Welcome to Physics afternoon video class. From this session onwards, we are going to continue our new lesson, Unit 6, Gravitation, in our Volume 2. Maintain separate note for second volume and write the important concepts what we teach in the online class, also in Zoom class. Now we continue our session. First thing, you have to know who introduced the concept of gravitational. That is Sir Isaac Newton. He only gives the definition and some examples related to the gravitational force, isn't it? Now, before his concept in 2nd century and 16th century, many scientists gave their knowledge regarding the gravitation, also the outer space concepts like our solar systems. During 2nd century, the Ptolemy, the scientist, introduced the concept of geocentric theory, which means where Earth is the center of the universe and all other planets like Sun are revolving around the Earth. That is known as what? A geocentric theory. He was suggested in 2nd century. Later, the 15th century, the Polish astronomer Nicholas Copernicus, he introduced the new concept of a solar system. What the Ptolemy said is wrong. So he introduced a new concept that is called what? Heliocentric theory, which means the sun is at the center of the solar system and all other the planets are revolving around the sun. So this is the concept of what? Heliocentric theory. So it was accepted by the all other scientists like Johannes Kepler and Tycho Brahe. All they are accepted the concept of heliocentric theory. Also a famous scientist Galileo also accepted the heliocentric model of solar system. Now you see this animated video, then you can easily understand the concept of geocentric and heliocentric theory.
When we left off with Aristarchus, he had correctly proposed that the Sun is the center of the solar system, rather than the Earth. But he was way ahead of his time, and the geocentric model remained in place for centuries. This model was perfected by Ptolemy in 2nd century Egypt. He improved on pre-existing models by finding a way to explain elusive phenomena, like the retrograde motion of the planets. This was when a planet would seem to turn around and go back the other way in the sky for a few days, before resuming normal motion. Now we understand very well that this happens because the Earth is passing the planet in its orbit, and will thus appear to move backwards. But back then, with the geocentric model, it needed some serious explaining. He proposed that planets move on epicycles, which are smaller circles that themselves move around the larger circle that is the planet's orbit. And this model was able to predict the motion of the planets with reasonable accuracy. But it wasn't perfect, so it was tinkered with, making things more complicated, requiring a different formula for each planet. This went on for centuries until the 1500s, when it just no longer made sense. It was at this point that a paradigm shift in astronomy was necessary. The first to suggest a heliocentric model since the time of Aristarchus was a Polish man named Copernicus. He demonstrated with great precision that all of the problems with the geocentric model instantly vanished if the Sun is placed at the center of the solar system. Objects closer to the Sun orbit faster, and the retrograde motion of a planet like Mars is now simply the result of Earth overtaking Mars at a particular time in their respective orbits. As we pass by Mars with a greater angular velocity, there is a moment where it appears to move backwards, just like when you pass a car on the highway and it appears to you to be moving backwards, given its slower velocity. Copernicus even estimated the distances from the Sun to each planet with great precision, using some ingenious geometric calculations. But there were still some issues to iron out. Critics of the heliocentric model had one very valid point. If the Earth goes around the Sun, the apparent position of the stars should shift. It would be several hundred years before we had telescopes powerful enough to see it, but this shift does indeed occur. It is just incredibly small because of the staggering distances to the stars. We use this slight shift today to measure the distance to certain objects in space. To understand why this works, hold a finger in front of your eyes. Then alternately open and close one eye at a time. Your finger will shift left and right depending on which eye is looking at it, because your line of sight is originating from a different location. Keep doing this as you move your finger away from your face. The shift in location becomes less pronounced with greater distance. If you try this with an object across the room, it already starts to be relatively negligible. Now imagine that the Earth being on one side of the Sun is your right eye, and the Earth being on the other side of the Sun is your left eye. A distant star will change its position in the sky, just like your finger, but the star is so far away that we need mechanically precise machines to measure the apparent shift. But we do have these machines in the form of modern telescopes, and because we know the distance from the Earth to the Sun, which is 1 astronomical unit, or about 150 million kilometers, if we then measure this apparent shift, we can cut it in half to get what we call the star's parallax. Then we make a right triangle with the Earth, the Sun, and the star, and simply use trigonometry to find the distance to that star. If you need to, check out my trigonometry tutorials for loads of information regarding triangles and angles. Parallax, among many other phenomena, strongly corroborates the heliocentric model, such that there has been no doubt in its validity in the past few hundred years. The Copernican revolution had a tremendous impact on human culture. The notion that the Earth goes around the Sun rather than the other way around is a fairly innocent claim to a scientist. One model fits the data much better than the other, and that's all there is to it. But the philosophical ramifications of this shift cut very deep. If the Earth goes around the Sun, the Earth is not the center of the universe. Other astronomers, like Giordano Bruno, reasoned that if the Sun is the center of this system of planets, and all the countless stars in the night sky are suns just like ours, possibly with their own planets, and perhaps even living creatures, then mankind is no longer the pinnacle of creation. The Catholic Church, very much in political power at the time, saw this way of thinking as a threat to its supremacy. As a result, Bruno was tried for heresy and burned at the stake.
I hope you all understand in the concept of animated video. Now, next we are going to see a very interesting law in physics which was given by Kepler in the year of 1571 to 1630, which means in 15th century he introduced some laws related to the planetary motion, that is the movement of planets in the solar system. So he introduced three basic laws related to the planetary motion. The first one is a law of orbit, or otherwise you can say law of ellipse. Then second one, law of area, and the third one is law of period. So these three laws are very important. Now you see this video and you can easily understand the Kepler's law of planetary motion.
Kepler's first law, the law of orbits. Contrary to the popular belief, planets don't revolve in circular orbits around the Sun. They move in elliptical orbits. So, what is an ellipse? An ellipse can be drawn using two pushpins placed on a straight line. Using a string, when the pencil is rotated around the pushpins, ellipse is formed. Kepler's first law states that all planets move around the Sun in elliptical orbits with the Sun at one of the foci. Kepler's second law, the law of areas. Kepler's second law states that the line joining the Sun and planet sweeps out equal areas in equal intervals of time. For example, the area swept by the Earth in March and April equals the area swept in May and June. Kepler's third law, the law of periods. Kepler's third law is concerned with the time period of revolution of planets. It states that the square of the time period of revolution of a planet in its orbit is directly proportional to the cube of the semi-major axis of the elliptical path around the Sun. For a circular path, t square is proportional to the cube of the radius of the circular path. For example, for Mercury, the length of the semi-major axis is 0.39 astronomical units, and its time period around the Sun is 0.24 Earth years. For Mars, the length of semi-major axis is 1.524 astronomical units, and the time period of revolution around the Sun is 1.88 Earth years. Observe that the ratio of the square of the time period to the cube of the semi-major axis is almost the same for both the planets. Summary. Kepler's first law states that all planets move around the Sun in elliptical orbits, with the Sun at one of the foci, not at the center of orbit. Kepler's second law states that the line joining the Sun and planet sweeps out equal areas in equal intervals of time. Kepler's third law states that the time period of revolution of a planet in its orbit is directly proportional to the cube of the semi-major axis of the elliptical path around the Sun.
Now, come to the end of this session, students. So, in this session, you discussed about heliocentric theory, geocentric theory, also a very important 3-mark question. So, Kepler's law of planetary motion. So, under this, you studied a law of orbit, law of area, and a law of period. I hope you all understand the introduction of our Unit 6 Gravitation. So later we discussed more concept in our future classes. Thank you.